I'm going to talk tonight about a container runtime management environment we've developed at CoreOS. It's called Rocket. It's something I imagine most of you folks have probably, or we at least hope you have heard of once or twice. Or, do I not have that right?
Yeah, just put it up so you can get to the people in the back.
How about that, people in the back? You like that better? All right. Okay, so anyway, Rocket's a container manager and that we've developed at CoreOS to address some of the concerns we have with existing systems that I'm sure you're all very familiar with. We built Rocket to address some of the process model problems that we encountered in running and trying to run production systems at large scale with Docker containers. So Rocket is not implemented as a daemon, and I have a couple of slides in here. I apologize that don't really fit. At any rate, Rocket is implemented as a simple command line tool so that we feel it is more composable and fits into enterprise workflows better than some of the existing solutions that we have some trouble with their flexibility and their process model. That's kind of a brief intro to Rocket. What I really want to talk about tonight is a new feature we've added in the 0.15 version of Rocket as we come towards our 1.0 release here in the very near future. To let us choose among models of executing containers at different levels of process isolation between other containers and the host system itself. So we're all pretty familiar, I'm sure, with the idea of containerizing applications, run them under Docker, run them in Rocket. Yeah, I had to use this slide. This slide and that one picture was pretty much the motivation for this whole talk. So I hope you guys like it a lot. At any rate, we've found a certain amount of difficulty in arranging to run things in containers exactly the way we want to at different levels of system protection and isolation. So we've added features to Rocket that we call Rocket Fly that essentially abstracts what Rocket does down to the distribution and verification primitives that we use to move containers around and runs them at a lower level of isolation and protection than you'd normally find in a container system. So here's how I'm going to illustrate this. I'm going to show you a couple of processes running in Rocket and a little bit of a demo. And we're going to look at them under the standard container isolation model, and then we're going to look at them under Rocket Fly and kind of see what we're trying to do here. And then I'll tell you a little bit about our motivations and why we built Rocket Fly. So if you give me just a moment, I'll switch over to a terminal here. So here I've got a pretty standard, in fact, I just spun it up, CoreOS system. You can see it's our latest beta version at 9.35. We ship Rocket on that, so we've got version 0.15 of Rocket that includes these new Fly features. So here's what it kind of looks like when we run a standard container under Rocket. I'm actually just have this in my history here. So I'm going to use the classic BusyBox example because it's going to give me a really easy way to show you the two different worlds we're looking at when we instantiate this container in two different ways. So first off, here is, you can see I'm instantiating Rocket, and I'm actually just going to pull a Docker image because Rocket can consume and convert to its native image format from Docker registries, from ACI files, which is a competing image standard that we can talk about here in a minute. When I run this, we get what we usually get, which is a little BusyBox container and a shell. And we can see very easily that I'm in an isolated process ID namespace. This is PS and top running inside of that container in the BusyBox shell. We can see that the network namespace is isolated in the ways that we expect from those of the host. So what we have there is, without a lot of sidelights about some of the neat features of Rocket as a standard container environment, like you may notice that we're running systemd inside this container. We have an init process that can deal with reaping children inside of the container, a classic problem in the Docker arrangement. And those are some of the highlight features of running Rocket as just a normal container environment with the normal Linux container primitives. But one of the really neat things about Rocket is we designed it with pluggable isolation primitives. And what I mean by that is we could run a Rocket container this way with the standard Linux container primitives. We actually have seen work from Intel to run Rocket containers, the exact same ACI images or Docker images, with full protection from hardware virtualization features by making KVM a stage 1 container environment. So you can take these same things that we're running with software protection in the container, swap out our pluggable stage 1 and run it with full hardware protection from the Intel KVM stuff with no change to the underlying image. That same technology, kind of going in the other direction on the continuum, is what we're doing with Rocket Fly. Now, at CoreOS, we build distributed systems, and we build a server operating system for what we call massive deployments. And that means that Kubernetes is something that's very important to our ecosystem and is the container orchestration system that we want to work with and provide really good support for. In some other talks and current discussions, we've seen Rocket adapted as the runtime for containers within Kubernetes. So when you schedule a job on Kubernetes, Kubernetes can actually use Rocket to schedule that work. What I'm going to talk about now actually turns that on its head a little bit. When you have a massive deployment of CoreOS systems, and they're in a Kubernetes cluster, each node in a Kubernetes cluster runs this little application called the kubelet. And the kubelet's an executable that manages container operations, scheduling of work on the Kubernetes cluster. Now, the kubelet is sort of specially privileged. It's a little bit difficult to arrange to run it inside of a container because it has duties to manipulate network routing tables, mount points, and schedule work actually on the host. So we build this minimal operating system, and we'd really like to ship the absolute barest possible exposure interface at each iteration of that OS. In addition to that, Kubernetes and CoreOS have different cadences or rhythms of updates, if you will. So what we wanted to do was we want CoreOS to be extremely easy to get up and running with Kates on. So in our beta and alpha versions over the last few months, we started shipping the kubelet as one of the stock binaries in the distribution. But for the reasons I just mentioned and the pace of updates, that doesn't actually work very well for us. We found trouble with different versioning between control plane and worker plane elements inside of Kubernetes. So in other words, we need to keep the kubelet and the API controller all at the same version. And that's a little bit difficult when we don't necessarily want to do an entire OS release at each Kubernetes update, and also possibly vice versa. So with Rocket Fly, we know we want the ability to discover, distribute, and verify containers in all of the ways that Rocket brings us. But we cannot run something like the kubelet with all of the protections that Rocket normally enforces and all of the isolation that it normally enforces for a regular process. So what Rocket Fly does is strip away much of the isolation system and leave you with the distribution and validation components that are so important to this system, so that we have signed and verified binaries that we're moving on and off of these systems as we do updates of the kubelet and distribute it through this. But we run on the host with access to host networking, to the mount table, and to the process ID namespace that the normal container isolation, as I've shown in this version of running an application under Rocket, doesn't allow. So if you let me spin up with just a little bit of command line difference, that same BusyBox container pulled once again from the same registry, although actually we're going to get it out of our local store because one never trusts the Wi-Fi, right? But we're going to run the same BusyBox container now with the Fly stage 1. Which will run it without all of the isolation that we've shown before, and then we'll take a look at what that looks like running under Rocket Fly. So in Rocket, I can always specify a particular stage 1 image, and as I mentioned before, we have a few of them, and we've seen some development and interest from the community in writing custom ones, and like the Intel work I mentioned, to actually take a container image and execute it as though it were a virtual machine with full hardware protection. One of the other stage 1s we ship, and it is the Rocket Fly stage 1. So invoking this BusyBox container with Rocket Fly, I'm sitting right back in a terminal in a container like I'm used to. I pulled the same image. I verified it through the same signature verification utilities that I normally would have. So I have all the same assurances about the source and security of this binary, of this application that I'm pulling. But as you can see, when I show you the PS tree, we are looking at the process ID namespace of the entire host. As you can see, when I show you the IP address list, we're looking at the network namespace of the entire host system. So what we have here is an executable delivered in a container to a container management system with signature verification, with discovery from known or named endpoints. And these are all things you can learn more about from the Rocket documentation, because they're a little out of scope for the talk. Nevertheless, able to do the basic host level manipulations that are necessary for something like the Kubernetes kubelet. So this is allowing us in upcoming versions of CoreOS to excise a large binary blob from our distribution, move it into what we consider a trusted and validatable distribution environment in the form of an application container image, or an ACI, an ACI as we like to call them. And distribute them with very easy automation to all of the nodes in a Kubernetes cluster, allowing them to run with just the level of host access they need, no more, no less, but enabling especially privileged applications like the kubelet. We can imagine other container management binaries, network fabric manipulation binaries, things that have to manipulate routing tables, any of these other host level items, running without breaking up the pattern of container distribution and validation that we've established. So that's kind of a rundown on Rocket Fly. Hey, a question. Okay, yeah, actually, I mean, that's an excellent question. You don't get any of the software-defined networking protections between port conflicts if you're running something with Rocket Fly that you do when you run a normal container under the normal Rocket execution system, where we then have a complete pod dedicated network fabric. So the whole point of Fly is kind of pulling things back out of that protection. These few special applications that might need, routing table level access. You?
Yeah, so this kind of.
It definitely bears a relationship too. The isolation is considerably different. Rocket itself, with its standard stage one, before we're plugging any other runtimes into it, we're just doing a regular Linux container style stuff, has a net equals host option that is actually much more directly analogous to removing those protections one at a time, like in the Docker model. So, good answer for that?
Yeah.
Okay. Oh wow, I would love to be able to show you that on screen tonight. We're not quite there with that work. That's a really interesting question. It actually reflects some of our discussions about this chicken and egg problem. But no, in fact, Rocket, and one of the things I want to say about Rocket that really does distinguish it from Docker is Rocket is designed, the whole motivation for not building a big long-running daemon was to enable it to integrate much more easily with existing init systems like systemd or Runit or Upstart on the Ubuntu platforms. It would be systemd on a CoreOS system. So to scope the answer down a little bit, it would be systemd launching Rocket as a service that would Rocket Fly invoke the kubelet. After that, the kubelet would then be invoking Rocket in its normal configuration to run containers in the familiar way that we're all very used to.
That part I get.
Yeah, that is probably outside the scope of the talk. It is a very intelligent question because, believe me, we are familiar with the sort of, which one do we hatch first kind of loop of that. But essentially, yeah, actually, let's leave that for possibly even another talk. Like, because I could go on about that for like a number of minutes, actually. And I think Dalton would be ready to, when he does his talk in a few as well, it could probably do the same thing. Anybody else? How about you? There are, that'll be in the very near future. How about that? I can't give you a date. We're pushing very close to what we're going to consider a 1.0 release and label it ready for production use. And we are advancing very rapidly to using it in production ourselves. It is interesting to note that right now the CoreOS website, the tectonic.com website are not hosted by Rocket containers, but built by Rocket containers. So we do have it in our own production workflows. And I'm the technical writer at CoreOS, so those are sort of things that are right up front and in my face all the time. There are a number of other projects that are using Rocket in our production workflows already internally at CoreOS. So I think that'll be real soon. Yeah, I don't want to go too far and make management or marketing unhappy, but we could, in many ways, you could consider O.15 and perhaps an O.16 and an RC for our 1.0 release. So we're getting very close to what you would consider the feature freeze or the complete set of features and interfaces for the product.
We good? Oh, I have another screen up here. That's fancy. Okay, yeah, as you said, I'm Anthony Yates. Sugu is over there right in the corner. So if you have any actual difficult questions, go to him. He's the co-founder of the Vitesse project, so he's the one who's been there since the beginning. I've been here about a year and a half. So Vitesse, as he said, is an open source MySQL clustering system and also a shard routing system. Developed at YouTube for its own needs, but it's been open source since almost the beginning. So I'll start with some background on what Vitesse is and some background on Kubernetes. I'll probably go through that quickly. It sounds like a lot of you have used it, but let me just take a poll. Who here has heard of Kubernetes? And who has used it? Okay, so pretty good crowd for Kubernetes here. That's my first time talking to a room who's had more than about 4 people who knew Kubernetes. And then I'll do a deep dive into how our Vitesse deployment was designed to run in Kubernetes. And also in general, what are the challenges of running a distributed database in Kubernetes? So Vitesse. I don't know if this is common knowledge, but I didn't know until I got there that YouTube started as a MySQL app and it still is a MySQL app. I've seen a lot of people on Quora or something who are saying, oh no, by now I'm sure their main database is on Bigtable or something, but no, it's still MySQL and it's running because of Vitesse that we're still able to do that. So there are tables for users, there are tables for videos, the kinds of things you'd expect in a typical relational website that was built in the 2000s. The first incarnation of Vitesse that I kind of call 1.0, we never really declared a 1.0, but this was when YouTube was in its own data centers. It started in the simplest form as a connection pooling proxy, and because of that, it was a really natural fit for Go, and we've kind of grew up with Go. We started before even Go 1.0 was out. But we really love that choice, and Stockholm Syndrome is very strong. And since then, it's Go obviously is becoming very popular with places like CoreOS who are concentrating on the cloud. And what happened next is YouTube itself moved everything into Borg, as you know, after it was acquired by Google. So Borg is this system that's shown on the right. You can see at the bottom there's a research paper published by the Borg team that explains a lot more in detail. But essentially what you can think of it if you're familiar with Kubernetes is Borg is what Kubernetes is based on. It's the attempt to produce something that can be used by everyone to give the same benefits that Borg has given Google. So the Vitesse team, as they moved into Borg, had to adapt their systems in order to run in exactly the kind of environment that Kubernetes is now forcing people to run in, where everything is containerized, everything is packed onto machines or virtual machines, and you don't have control over where these containers will be, how densely packed they will be, and you don't have control over when they'll be destroyed because some other container has higher priority, or just because that machine needs to go down, or just because some gamma ray came in and said, flipped a bit and said this container should no longer run. And along with this, Vitesse started to evolve. So for example, originally we had shard routing logic inside of the YouTube app. We moved that into Vitesse in a much more general way because engineers love to solve problems in the general way instead of the specific way, as long as the management will allow. And so there's a lot of features also that came in at this time to just help kind of all the lessons that the Vitesse team was learning about how to run MySQL at scale. We kind of incorporated into this project again as in a general way as much as possible. So I won't be talking too much about all those features that are, but you can look at the vitesse.io website and find out more about those. And then what happened next is YouTube grew and Vitesse had to grow with it. So these are just some public stats of, you know, 1 billion users, a whole bunch of video uploaded. This is a real-time versus upload rate of 24,000 seconds every second. So you can think if you wanted to watch all of it as it's being uploaded, you need 24,000 TV screens. I like to think of it kind of like that room in the Matrix where the architect lives. And an important stat is that 80% of the views come from outside the US, which means we can't afford to say, I'm going down for an hour between 1 a.m. and 2 a.m. For a database update. We can't do that. We're going to make a lot of people angry in Thailand or something. And the YouTube app has been evolving a lot, which puts a lot of pressure on the database to support things like having your schema changing all the time and having your database access patterns changing all the time. You know, we get teams within YouTube who come to us and say, I'm about to double such and such amount of traffic that comes from this component. Is that okay? And we have to look into, you know, how to address that. And another thing that came with this growth is we developed this technique of live resharding. I've done a talk about this before, the slides. You can see also on vitesse.io. The main point there is that you can go from n shards to 2n, 4n shards with no user visible downtime. So everything is happening in the background. Then you do a switch over that takes a few seconds. Nobody notices. So this is now where we get to the point last year, what I call Vitesse 2.0, which is kind of the version that we're pushing towards release right now. Vitesse was always open source, but we were mostly focused on making Vitesse great for YouTube and kind of had it open source as a way of just kind of showing the industry what we're doing, and hopefully they can show us what they're doing and we can all learn from each other. But what we're doing now, what we did now last year in 2015 is we said, hey, it looks like there's a place for this to actually be like a self-contained product that people will run for themselves outside YouTube. And so we put a lot of focus into preparing Vitesse for that last year. So there's some kind of milestones here year to year. If you had heard of Vitesse in 2014, you would have had a really hard time trying to use it for yourself, and our answer would be, we don't have documentation, look at the code to see what it does. In 2015, we now say, here's a step-by-step guide to run it on Kubernetes. Here's some few simple commands that you run, and here's how it all works. And we have some, you know, some nice design docs that say what we're thinking when we made these decisions. And then what's coming this year is we're moving towards making this really more of a drop-in thing where you can say if you were using MySQL before, even in an unsharded capacity, the vision is to go to where you can go from unsharded MySQL to sharded Vitesse without having to change your app. Right now, there are some minimal changes that you would need to take, and I'll show a little bit of an example of that later. So just to give you a baseline, I'm not going to, again, this isn't exactly a talk about Vitesse, but I want to give you a baseline of the concepts of what's contained in Vitesse. So if you imagine your pool of app servers over here, you also have some batch jobs maybe. The entry point to Vitesse is this component that we call VT gate, kind of the gateway. And what happens is the app servers don't need to know anything except how to find any VT gate. It's a pool of stateless servers. Then we have those VT gates, which routes to VT tablet. And those are a sidecar process, if you're familiar with Kubernetes terms, that sits on top of MySQLD on the same machine and kind of does, kind of controls the behavior of MySQLD and isolates it and provides forwarding of queries in Vitess form through into the MySQL. Then at the top, we have VTCTLD, which is the admin interface for the whole cluster. So you issue commands into VTCTLD. It manages all these VT gates, VT tablets, and creates the states that you want. And of course, etcd is there, which is what we use to store cluster state, distributed configuration for the whole thing. Okay, so I'll do a really quick Kubernetes just for the few people who are not using it already. Kubernetes, sometimes abbreviated as K8S. I think of it as a glue for distributed apps. So it provides a lot of services that when you're building a distributed app or distributed system, it makes these tasks a lot easier. Another way of looking at it, some people have described it as an operating system for distributed apps. So if you can wrap your brain around the analogy there, it's a good way of looking at it. And one really powerful thing that it does now with the current market that we have with lots of different cloud providers is that it abstracts away the particular cloud platform that you're on for a lot of different things: network configuration, load balancers, creating the VMs in the first place. I guess you can think of it similar to things like Puppet and Chef, but it's an even larger platform that's kind of all in one piece. And if you were paying attention back on the Borg slide, that diagram over there should look really familiar. That's not an accident. It's because Kubernetes is designed by a lot of the same people who worked on Borg. And so just to get some baseline terminology also, the node is what they call the physical machine or VM that, as the previous presenter was talking about, it runs the kubelet, which then allows Kubernetes to launch jobs on that machine. Containers, you guys know what containers are. The pod is what the Kubernetes uses as the scheduling unit. So everything in the pod gets scheduled in the same place. And you use that for grouping containers together when they need to be on the same machine. Volume is just like in container language, is the storage that gets mounted into the container. Replication controller is an important one. It's a kind of an agent that sits out in Kubernetes land. You don't really see this running, but it lives in Kubernetes land, and it does your bidding, and you tell it to ensure that there's always so many copies of a particular pod template, and it will maintain that state for as long as it exists. And then services in Kubernetes are used for discovery. Oh, sorry. Yeah.
So you said
well, so we run these on Container Engine, which is Kubernetes on Compute Engine. So those are Compute Engine VMs that are running the kubelet.
this is your own VM.
Oh, this is just a kind of a definition of how Kubernetes works. So it's a VM in the normal sense of any VM that you. Nothing special about this VM. It's just running the kubelet daemon. And then lastly, services are used for discovering things in this distributed environment, figuring out what's the host and port that you need to connect to. And it also does some simple load balancing and proxying to give you one IP address that will load balance onto multiple endpoints. So with that, what is special about running databases on Kubernetes? Has anyone here who uses Kubernetes, have you tried running a database on it? And keep your hand up if it went well. Okay, one guy. What do you run? Okay, and how many servers? Okay. So there's this concept that's been parroted a lot in Kubernetes land, which is of pets versus cattle. This is I kind of first saw it from this blog post. You can look down there. So So it's this idea of, if you're a kid and your dog Scruffy dies, your parents say, we'll get you a new dog. And you say, no, I don't want a new dog. I want Scruffy back. That's a pet, right? So if your server is like, no, your server goes down, if it's your database, you're not going to be happy if someone says, oh, I've got this other server here. No, I wanted that server. So thinking about it in terms of cattle is different, right? You have 5 cows over there. Somebody says, one of your cows wandered off, but we found this other cow. Okay, whatever. And so that's kind of the philosophy that Kubernetes wants you to live in, and it's the same kind of philosophy that we're used to running in Borg. And so when you try to introduce the idea of databases, persistent storage in the cattle philosophy, it raises a lot of questions of, how do you keep databases from falling apart and forgetting everything, right? Before you look, I'll save you some time. The domain name cattledb.com is already taken. It's exactly what it sounds like. It's a CattleDB. So why do we even want to run databases in Kubernetes? One of the big reasons is we love how it runs in Borg. It gives us a really easy way to scale when we need to scale. It gives us a lot of features like I was talking about, that glue for distributed apps, that you don't have to worry about any of those things anymore. But then why is it hard? One thing is when you decide to scale your database horizontally, you now have thousands of endpoints perhaps, and you need to make that look like one logical database to your app. That's where things like Vitess routing layer comes in. I'm not going to be talking too much about that, but that's one of the issues that you have to address. And of course, this main issue of the fact that pods, which are the scheduling unit of Kubernetes, are by design not durable. And if you say, if you make a bug on the Kubernetes thing that says my pod died and it didn't come back, they're going to say pods are not pets, period, close the issue. And so in Kubernetes, durability comes from pools of replicas. You can't have a single machine that you expect to provide durability for you. So I want to go through some options. Well, what are the options that Kubernetes gives you to store your data? Because that's the big question with a database, where's the data go? The first and simplest one is empty dir. Empty directory is an empty directory on the local machine. And the key is that it's ephemeral, which means if the scheduler decides that pod's going to move somewhere else, all this data gets deleted immediately. It's gone. There's a host path, which maybe if you're looking at this for the first time, it sounds like the solution to this problem. Host path, if you put your data there, it's on an actual directory on the host file system, and it will stay there when your pod goes away. If your pod comes back, that data will still be there. That sounds great, except that it doesn't work because your pod might be scheduled on a different machine, in which case the data you left behind is totally useless. And in a reasonably sized cluster, it's actually more likely that your pod will never get rescheduled back onto the exact same place. It probably got moved because of some real reason, like that machine's going down. Then there's options like persistent disk, elastic block store. These are persistent disks that are outside of the Kubernetes node, so they have their own systems that maintain durability of storage. And Kubernetes lets you plug into these and say, mount one of those EBS volumes into my pod. And this works really well for if you have a handful of servers, or if you have a fixed amount of servers, because you can go and create these volumes and hook them into your pods, and maybe launch each pod with a replication controller to make sure that one pod stays around. But it doesn't work if you have a flexible number of pods making up your database. It doesn't work if you need to create these on the fly and have them allocated with an intelligent scheduler. So this is where persistent volumes come in. Yeah.
May I ask why not?
Which one? Why not?
Why?
Yeah, you could make you could use your own automation outside of Kubernetes to create the EBS volumes, and then use your own templating system to inject them into pods. Persistent volumes is the abstraction of that. So it is that, but it's the abstraction of that in Kubernetes language. So yeah, what do? Is they had this new feature, persistent volumes. There's an analogy here. Persistent volume is to EBS as the Kubernetes node is to the VM it's on, which means when you're creating these persistent volumes, you're creating the availability of the resource. You're not creating a particular thing. The persistent volume claim is the equivalent of the pod. So the persistent volume claim is saying, I want a particular disk, and I care what's on this disk now. And when I refer to this disk later, I expect it to have the same data on it. That's the claim. And what this does is it decouples your compute resources and storage resources. They're accessed across the network, but also there can be separate schedulers in Kubernetes that that load various workloads onto CPUs and load workloads onto disks. So this is nice for, again, solving this problem of kind of creating a pool of volumes instead of having to do it manually or do it from an outside automation. The problem is if you're using a replication controller, how do you give each replica that's created by that replication controller a different persistent volume claim? Because if you have, for example, in MySQL, 5 replicas replicating from a master, each one needs to have its own storage so that it could store its relay logs, store its particular position in the replication stream. Each one is different. And it turns out that with replication controllers, you can't, or at least there's no way to have Kubernetes do this for you. And that's because the replication controller will only give you n exactly identical copies of a particular pod. So there's no way to tell it, I want this pod to use that volume claim, I want this pod to use that volume claim. There's a new proposal that's being debated right now. You can see it's 18016 on the Kubernetes repository. And what this is going to do is introduce what is essentially a feature that Borg has that we've been relying on that they decided to hold off on at the beginning because they don't like the implications that it had in Borg for doing updates and other features. So they want to try to do it better. And so that's why there's a very heated discussion going on how to exactly to do this right. But the main thing that it will give you is instead of a replication controller, it'll give you something that will maintain a pool of n copies of something where they're almost exactly the same, but each one has a unique identifier that not only does each one have a different identifier, but it kind of, in the ideal case, will guarantee that there aren't 2 copies of the same thing with the same identifier. So you can use this to say, for example, if there is a persistent volume claim number 1, 2, 3, I want to assign my pets from the pet set to one to each of those claims. So that would solve this problem and make it really easy to scale these replicas, although this feature is still in development. Okay, so now I just want to go through how we put these options together and the decisions that we made when making our Vitesse deployment in Kubernetes. So just a reminder of what Vitesse looks like. So now let's translate each of these things into the Kubernetes terms and how we're going to run it. etcd is the first step in our process. It turns out that etcd is itself a database. And so it has the same problem of it really wants to care which instance is which, and Kubernetes doesn't let it. I talked to the etcd guys about, how do you recommend running it in Kubernetes? They said to do one replication controller for each instance, which works, but then it's a similar situation where you put yourself in the game of making your own automation on top of the system that's supposed to be doing that work for you. So I came up with a harebrained scheme that it basically uses on the right there, you shouldn't be able to read it, but it's a complicated shell script that makes each replica do something different than the other ones by taking advantage of etcd itself, which provides coordination, and also taking advantage of the built-in DNS features in Kubernetes, which will let you enumerate all of the replicas created by the replication controller. So with those two together, you can use the etcd serve discovery mode to do your bootstrap without having to rely on anything except Kubernetes as your coordination. So I sent this to the etcd guys and said, what do you think? Is this crazy? They never responded. I'm assuming that's bad news. But it's been working so far, every time I run my tests. Mode? Yeah, SRV, the serve record. So it's what's called a headless service in Kubernetes, where instead of giving you one IP, it gives you the list of all IPs that match that domain name. And so it uses that to do discovery. And then this is on the right, the interface web UI for our administration console, which is VTCTLD. This one is extremely straightforward. It's the same as any guestbook sample app in Kubernetes. You create a replication controller, you have a service, and one nice thing I want to point out is these features kubectl proxy and port forward. These are really nice for getting kind of admin access into individual servers within your Kubernetes cluster without having to expose them as a public IP on the internet. So these will do tunneling for you over HTTPS, and it will do authentication and all that good stuff. So this is how we've set up our examples to let you connect into VTCTLD. And then VTGate, which is this stateless pool of entry points. Again, the client only needs to find any one of these. And the nice thing about Kubernetes, one of these things that I was talking about that the platform does for you, we have these pool of VTGates out there. This is an example client connection call. All it needs to do is refer to the DNS name, host name VTGate, which was automatically created in the DNS system by Kubernetes. And then that resolves to an IP, which is a load balancer, which load balances across the pool of VTGates. So it's really nice for the app layer that this is really all they need to know to get into Vitess. Now the hard part, which is the database itself. This is where we have a pod called VTTablet, which contains VTTablet, the process, and MySQLD, the process, each one in its own container. What we use for this actually is an empty directory. And the main reason for that is because it's actually the same thing that we do in Borg. We use an empty directory, which means when the pod first gets scheduled, it's empty. It has no data. So where does that data come from? What we do is we have a backup restore feature, which will pull the latest snapshot from Google Cloud Storage, NFS. You could also write a plugin for things like S3. We haven't written that yet, but pulls the latest snapshot, and then it will automatically connect and catch up on replication to the latest point, and then it'll go and start serving. And so why not a replication controller for these replicas? Because we want to have n copies of these that are all replicating from the master. One reason is that, again, I was saying we designed this for Borg originally, and in Borg you have that ID system where it tells you, okay, tablet 3 went down, another tablet gets brought up, and Borg tells it, you are tablet 3. Then it can go into things like the records of etcd, and it knows if there's a record referring to tablet 3, that's mine. I should take that over and be tablet 3. If Kubernetes doesn't tell you a unique identifier, then you're on your own to figure out which role you're supposed to replace and which guys are still running. So that's more work that your own system would need to do. And so that's why we haven't used a replication controller right now. I have a proposal that would make this possible, but it would require some reworking of the structure of data we store in etcd. So that's possible, but at the same time, if this pet set proposal goes through, it would be pretty much unnecessary. All right, so with that, I hope you have a little idea of the, Yeah, we just threw a pod out there. So which means if the process is crashed, it does restart the containers. But if that node goes down, the pod will disappear forever. And we've had people trying this out and noticing that. I was really impressed at the detail to which this one guy went to try to kill everything at various levels. Yes. Yes, again, you can have an RCU size one for each one. The idea of the pet set proposal is to address exactly that use case in a much more elegant way. Any other questions at this point? Right. So I want to end with just some sneak peeks of what we're working on this year. As I mentioned before, we have this vision of making it more of a drop-in thing where you don't have to change your app. So this is an example of what you would have to do now that's a little bit different than using directly MySQL. We have on the green there, you're sending this query, but you're also telling Vitess, okay, this query relates to user ID N. And Vitesse goes and figures out what shard user ID n is on. And the nice thing, even in the current state, the nice thing is that you can use Vitesse live resharding, and the app will have no idea that that's happening. They will have no idea that user ID n is now on a different shard, or that it's being switched back and forth as you're testing. And of course, the site will not notice that anything is having downtime. But the next phase that we're working on, Sugu is actually the one pioneering this. Concept that he calls Vindexes. So you can think of a Vindex as kind of a meta index. So an index on a table in MySQL lets you look at only some of the rows to find what you want. It tells you, okay, if you want values between 5 and 10, you only need to look at these rows. You'll find them all. You can skip all the other rows in that table. A Vindex is a similar analogy where it says, oh, you're looking for values between 5 and 10, you only need to look at shards 2, 7, and 8. You can skip all the rest of the shards. So that's what the Vindex is at its most basic. And so what would then happen is that green stuff goes away, and it looks just the same as any other, sending a query into MySQL, any kind of PEP database interface. The nice thing here is that what will happen then is we already have the first phase of this working is where, okay, based on this query where you have where user ID equals something, VTGate is actually looking and analyzing that query, and it'll figure out what user ID you're referring to. Then it'll do the hash for you. Then it'll figure out what shard it's supposed to belong on and route the query accordingly. A nice thing to note is that not only can it do figure out when you have the user ID in the query, it can also route queries where you don't have a user ID in the query. So how does it know which shard to route to? For example, you might have a video ID in the query, and VTGate knows through its Vindexes what videos are owned by what users. And so it can figure out the user ID of that video and then route it to the correct shard without you ever telling it what user ID you're talking about. So that's the in-progress work. Another thing we're working on is automated master recovery. So we get this question a lot where they say, if the master goes down, is it going to fix itself automatically? And we have to say, well, we have a tool internally that runs that, but it's not really, it's too tied in to the internal systems for us to make sense to open source it. And so what we're doing is we're working together with this project called Orchestrator, which does exactly the same thing that our internal tool does. And we're trying to integrate Vitesse with it in the same way, where Orchestrator is responsible for managing replication. It also has its own interface that lets you set up hierarchical replication, all kinds of complicated things that Vitesse doesn't care about. All Vitesse needs to know is once Orchestrator has picked a new master, after it automatically detected some down condition, it just needs to tell Vitesse who the new master is. And the reason for that is because we want to make sure there's only a certain downward flow of information without feedback to make sure there's no split brain happening. But that's the kind of integration we're working on. Another thing is that Orchestrator, if you're using it by itself, you have to kind of seed it with saying, okay, these are the host names of the first few MySQL instances, and I want you to crawl the rest of that. Vitesse already knows through its data stores and etcd where all the servers are. So we can skip that step and have Vitesse directly tell Orchestrator, these are all of the servers, and go and start monitoring them and controlling replication. So with that, here are some extra links. We'll post the slides somewhere, I guess, but I'll open up for any questions. So one of the big reasons is, one of the big things is that Borg is more complicated in its scheduler right now. They're moving Kubernetes towards that direction, but for example, Borg is better at ensuring rack diversity and making sure that if you have X replicas that they're not all on one machine and they're not all going to go down at the same time, right? So if we're living in this world where if all of our servers went down at the same time, we would lose data from the last since the last backup. But that never happens because it's, the probability of that is minuscule because of the way Borg intelligently schedules across a wide number of machines. And so that's a little different in the Kubernetes land because the schedule is not that sophisticated. it's probably safer at this point to rely on things like EBS for your data durability. The other thing is that Borg allows in-place upgrades. So if you want to do like switch out the binary to a new version, or if you want to change the flags, you can take down that job, bring it back up in the same place with the files still intact on the local machine. In Kubernetes, it may be possible, but they really discourage that. What they want you to do is imagine this pod is totally trashed and you're creating a totally new pod that happens to be doing the same job. And you have a replication controller doing the puppeting and taking one down and putting one up. So there's no way in Kubernetes to do this in-place replacement. That's another reason why you would prefer to have your data storage off of the pod machine. Any questions? So before the Vindexes stuff, you can get data from multiple servers in the form of either telling it specifically, I want data from shards 2, 7, and 8, or telling it, I want data from all shards. And what it will do is then, it's called a scatter query, where it will send that same query to every shard and combine the results for you before it returns them. In the new world, it will be much more intelligent on going only to exactly the shards that could possibly have data relevant to your query. Yes, VTGate is the one that's merging. Yes, we support transactions which are, you begin a transaction on VTGate. If that touches multiple shards, it will open transactions on multiple shards. What we don't have right now is cross-shard transaction consistency, where you have 2PC, but that also is something that's in progress right now on Sugi's plate. When you say that, you mean transactions, yes, or while you're in progress is resharding? So while you're in progress of resharding, what we do, it's a whole nother talk on resharding, but we prepare the new shards, and we have filtered replication, which is our own process that we run to send all the transactions from the old shards to the new shards while the app is still pointed to the old shards. And then you do this quick 5-second thing where you pause the old shards, wait for the new shards to catch up, switch to the new shards, and then re-enable writes on the new shards. So that's the, like 5 seconds of read-only time where writes at that point will either queue up or they will get dropped if the queue is too big. Back there? No, not Vitesse on Kubernetes. No, nobody's using it. I can neither confirm nor deny whether there are intentions. Any question? Yeah. Okay, yeah, you guys are good. So finding exactly the weak points. So internally for schema, what we do is I don't know what the common term is, but Facebook does a similar thing where you do your schema change first on, if it's a large one. If it's a small one, you can just put it through the replication stream. But if it's a large one, you do it on a server that's totally offline, not serving anything. And then you do this process where you copy that into new ones and swap it out as you go. So that's what we do internally. We have a tool that runs that, but again, that tool is not really worth open sourcing in its form. So we're planning to re-implement it as an open source version that works on top of Vitesse. Yes, mostly because of this issue where, like we were saying, we internally rely on this mechanism. So we did the same thing externally where when the pod comes up, it's totally empty. It relies on this Vitesse integrated backup restore mechanism. And what we did is we wrote it as a pluggable system. So we have plugins for NFS or for Google Cloud Storage. You could write, it would be like 300 lines to write one for S3 if you have an account. I have an account, but it's my personal credit card, so I haven't done testing on it. Any other questions? Oh, yeah. Yeah, our wire protocol is actually different. It's we use gRPC, which is a another project similar to Kubernetes that's a Google technology being open sourced. So gRPC is based on Stubby, which is Stubby is the RPC protocol that runs basically everything at Google. The Stubby team made gRPC as kind of the next generation, and they decided to make it in the open source. So our open source Vitess uses gRPC for all of its connections from the client into Vitess and also inside of Vitess. So our client level then is the one that translates between, if you were going to switch out your for Vitess, you would do it at, for example, the client driver level. So maybe PDO, for example, we're working on, you would just switch out the driver to say use Vitess instead of MySQL. That's it, and thank you. So we'll take a from the Dalton, and I'll take from here.
All right. Thank you guys for sticking around. So, like was said earlier, for the last month or so, I've been sort of playing around with bare metal, which is an interesting domain to me for a software engineer to be playing around with. Just to be clear, I want to talk about like physical hardware, and that means that it's not a dedicated machine that someone has set up for you and given you like SSH credentials to, and like a bare metal in that sense. We're talking about like, I hand you a piece of hardware, and I go make Kubernetes with TLS like authentication work without a human being involved. So that was sort of my goal, setting out to play around with this. So we just have some machines. They don't know anything about their network. Their disks are probably not configured correctly. They don't have any software or kernel installed on them. They're just machines that we want to start with. And with CoreOS, there are a couple of important utilities or tools you can use to configure your systems, chiefly ignition configs and cloud configs. And I'm going to take advantage of those to do some cool demos, hopefully. But the first piece that we needed was a small configuration service that would serve up the right configs at the right time. Because if our goal is to assist with Pixie booting machines and then to serve up ignition configs and cloud configs, we need a tiny little service to like just provide those configs at the right time. So in demos today, I'm going to try to boot up 2 clusters for you, one Kubernetes cluster and one etcd cluster. And we're going to use Docker and Rocket containers to do that. So the setup looks a little more like this. Once you have a config service involved, you have some network in some data center, or for me, it's like a little stack of machines in my house, or we have a couple stacks of servers at the office and a big rack as well. These machines can talk to a config service if we want to do configuration, and there's an external DHCP service and TFTP service because it seems like a lot of people have their own setups for this, or I've talked to people who have like implemented their own TFTP servers and stuff, so I didn't really want to like delve in and prescribe a solution that would like take over your DHCP. So in this setup, the config service assists, and you can run your own, whatever your existing Pixie setup is now, you can continue to use. So the first sort of piece that we need to figure out is like, how do we figure out what to give the right machines? And a simple way to do this would just be like if our config service could like know something about the machines that are actually booting. So I'll come back to the actual Pixie booting start of the machine's lifetime in a little bit, but first I want to just talk about if we already do know the machine attributes, we're just going to have a config file like this that you use when you start the config service, and you can identify a machine by its unique identifier from firmware. Is this readable? It is readable. And by its MAC address. And this is actually doing an AND operation. And the config will support more advanced matching. This will do, if you don't actually want to use machine attributes, if you have some sort of, you could use any sort of free-form tags to match machines that you like. Or if you want to just have a default profile that all machines will get, you could just like leave off the requirement so tags. So that was the very first piece is we have all these sort of resources we want to serve to machines. Let's match them by some simple tags. Now, let's talk about the data that we want to serve. Right now, this is backed by a file store. Longer term, I imagine this could be backed by etcd, so you could have like a multi-node deployment of a configuration server. But right now, it's kind of easy to keep the collection of files that you want to configure machines with in version control, just for testing stuff out and booting Kubernetes clusters. There are 3 pieces of information. Boot configs, that's sort of used loosely because we support a bunch of different network environments, or the goal is to support a bunch of them. Ignition configs, which I'll talk about in detail, and cloud configs, which I'll also talk about. So let's first go into sorry, back up a little bit. We match machines by tags to a specification, which is just a place we dump all the data about what we want that machine to come online as. So we can say this particular machine with this MAC address is going to become a master node in a Kubernetes cluster. This one's going to become a worker, and this machine with this other unique identifier belongs to a separate cluster completely. So if we can describe that all in one config, we can make a little bit of progress. Most of you have probably played around with cloud configs if you're at a CoreOS meetup, I would imagine. You notice the fixed IPs in here because we're on bare metal, so there's not like a immediate solution that allows you to substitute in values. So we're going to just start out by putting some IPs in there. This is for an etcd cluster with 3 nodes. Ignition. Maybe less of you have heard of Ignition, but it's a really powerful configuration tool that we're kind of sort of hoping to move towards or favor a little bit more heavily. The chief difference is that with Cloud Config, you can start like particular units. Like it does well at supporting named units and configuring etcd2 like this, and it's somewhat CoreOS specific. It runs after systemd is already started. So any sort of unit files that you drop on disk or any writes that you do will happen after the system's already started. For networking configuration, that means you usually have to like end up rebooting the machine or things like that. With Ignition, it actually runs from the init rem disk. So it's running much earlier. You can write all your files to disk to configure the machine completely, and then systemd takes over. So ideally, we could start slowly moving pieces into using Ignition configs. Right now, the examples I'm going to show are sort of a hybrid of the two, as I've started to move network configuration into Ignition, because it's the most critical piece that you want to have running or configured before the machine starts PID1. So those are just the two configuration pieces. Ignition, Cloud Config. We make use of both. Ignition is highly preferred or preferred going forward. Now the actual booting part. I said that the config service could support network booting environments. The main ones that I've played around with is iPXE, because it can load HTTP configs, and with PXE you can chain load into iPXE. We could also support actual TFTP endpoints. And PXE Core is a fun Go project that actually sort of bundles in a TFTP and DHCP server. Actually, it's a proxy DHCP server. And GNU Grub is another one we're looking at supporting. And we're viewing this, or I'm viewing this as taking these resources and just rendering them as configs for the different network environments. Because really, no matter which of those network setups you're using, you're just choosing a kernel and you're choosing some kernel options. So that was why that was part of the specification. And it just, yeah. And we render those correctly as menu entries for the different network systems. There are endpoints for each. Now, you're not going to watch me actually set up a PXE and DHCP server today, because I can do, oh, I should have showed that slide. That's the slide that lists all the network boot endpoints. There for a reason, I guess. This lists the current state. Grub is upcoming. So we have this config service. It allows us to treat these things as resources. It's a containerized service, so I can run it within virtual bridges on my machine, which is what I'll do for demos today. I can run it on my host to set up, to run it on my network if I want to set up real machines. And then if you have, in the real world, I guess, you could run it on a dedicated node, or you could run it on Kubernetes if you want to have a standing Kubernetes cluster that helps to boot other Kubernetes clusters, or maybe it helps to boot itself as machines come online and stuff. Because the other thing you have to worry about is that CoreOS instances should ideally be receiving automatic updates, and they should be able to reboot at any particular time and come back. One other thing I forgot to mention about Ignition is that it usually just runs once. So you drop your files on disk, and then on subsequent reboots, it doesn't need to run again. Let's dive into my examples. So like I said, I'm not going to actually set up all these servers, because I can just use either a Docker container, or I can use an ACI to use Rocket. And I'll do both of those, actually. The important parts to note here, I'm using DNSMask just because it's a cool utility that can run these components all together. So the important bits to notice here are we have this helper, CoreOS DNSMask. It's literally just a quick helper that helps you run DNSMask without changing your host configuration. I specify a DHCP range for the DHCP server I want to run. I specify a TFTP server. I already have a UNDI only kpixie chain loader in there so that older Pixie clients can chain load into iPixie. And then the whole job of the netboot setup is to point to the config service at the end of the day. And right now that's going to be on a known address because this is within the Docker 0 virtual bridge. Here it is in Rocket. In Rocket, we're going to use CNI to set up a virtual bridge for ourselves. And it's a very similar setup, except it's running an ACI. You specify a DHCP range, a TFTP server, and you point to the config server. So you just need to get to the point of loading HTTP configs and having DHCP point all your machines to our config service. Demo. All right. So those commands are a little bit long, so I have them prepared. So you can check out this project also to find all these commands. And the other piece of this project is actually doing guides for doing this. So don't feel like you have to copy anything down. So the first thing I'm doing is I just have a little script that's going to create 5 VMs on libvirt, and they're going to be bound to the Docker 0 virtual bridge so that I can actually run VMs and containers on the same network to demo how this is going to work. And these machines are configured to Pixie boot. So I'm using virt manager for this to view the machines. And if I open up one, you can see that it failed to Pixie boot because it's just on like a lonely little network with a bunch of other VMs, and it has no idea what to do. So the next thing I'm going to start up is the config service, which is just another container. The import part, it's loading that config.yaml file I looked at earlier and some data about basically the cloud configs and init configs I want to use. We're going to run that. And if I hop over to Chrome, you can probably at like the cloud config that it's going to use. How that's hosted. It's just a simple endpoint. So this is the configuration for the master node. You can put arbitrary query parameters here to match by different tags. It's fairly straightforward. And the way this is working is that this is actually almost straight from the CoreOS-Kubernetes project, which has some great configurations for setting up with cloud config. I'll get back to that actually. And then the only other piece is that now that the config service is running, I just need to run DNS mask so that I can point all of my clients to it. So I'll run one other container. That's over here. I'm going to power them off. Power off those 5 VMs at once. Versh and I have different ideas about what power off is called. They call it destroy. And we're going to start them now. Yeah, ignore the fact that it's not really destroyed, it's powered off. And those are now, they should be booting, and this guy's still alive. So maybe the helper script isn't working. And then so that this is more exciting, I'm going to open up a couple of these. I'm only using the first 3 nodes. So what I'm setting up here is a Kubernetes cluster. Node 1 is going to run the master and the control plane. Node 2 is going to be the worker, and node 3 is just a dedicated etcd node. And this is, obviously, that's just completely just the configurations that I chose, so you could sort of put whatever you want here. The ignition config in these examples is just ensuring that each of these 3 nodes has a known IP before systemd starts, so I don't have to do any restarts or anything like that. And right now, I'm using cloud config for the rest so that I can just use the existing CoreOS-Kubernetes scripts, cloud config script. And so this proves, I guess, that that I haven't cheated and it hasn't come online yet. It usually takes 2 minutes in my tests. Why does it take 2 minutes to start? Well, that's a good question. This is setting up Kubernetes, setting up the whole control plane. Before it does that, it's waiting on the SED nodes to come up, so sometimes node 3 takes a little while. Sets up the control plane, and then the worker comes online. And once the Kubernetes components are set up, and all the kubelets running and the kube proxies are running on the nodes, it's also going to go ahead and install the add-ons, like DNS add-ons, and other goodies. There we go. We have a node. All right. Get pods. All. So you can see at this point, the only thing we're waiting on is the DNS, the 4 replicas for DNS to come online. And maybe I won't wait on them. I'll just continue with the demo. Oh, they're back. So we actually have the full Kubernetes setup with the add-ons, working. And just to prove that, a couple of other configs. My prepared hello world. So now I'm going to just create a service definition and create a couple of replicas. This is a hello world. You'll see it momentarily. It's very exciting. So now, since I said that node 1 and node 2 were both running the kube proxy, I should be able to either one of those. They happen to be running at 172.17.0.21 and 22 because that's what the network D told them to be, and this just says hello go. And there are different shades of blue because there are multiple replicas. So yeah. Yeah. Let's destroy that now. Now we can do create rocket. So this is going to create 5 VMs on the rocket, ACNI network. It's very similar. And permitting. I might just hop ahead. I'll just show you briefly. We can create those 5 VMs on the Metal Zero virtual network defined in CNI. We can run the exact same Docker image. It gets converted on the fly as you pull it down into an ACI or ACI. And I run those with Rocket. It's the exact same application. The final piece is just running an ACI that does the same DNS math work. And this example would have booted a 3-node ZD cluster. Hop back to my presentation. It works. There are docs. You can try it all out. And also, this works on actual systems. This picture is one of my favorites because this was at like 3 a.m. This was my first ever actual bare metal install of Kubernetes without human involvement. Just power them on, and then kubectl was working about 2 minutes later. So this stuff is possible. Where do we want to go from here, I guess? That's probably the most exciting part. The first bit of code hit the web for this project, I think it was Christmas Eve when it was available on GitHub, and the 0.1 release was a few weeks ago, and our first blog post was on Friday. So this is all very new. It's sort of a proof of concept of just like, you can get a machine to come online. When it comes online, it's already configured to be a Kubernetes cluster. That's normally the point where you would like attach some SSH session and start configuring or run your Ansible scripts or whatever. But if we can just drop the right files, the right systemd units on disk, you can configure a whole cluster like this. So where do we want to go? You probably noticed there were a lot of fixed IPs in those examples. The solution to that is to build a metadata service. Ignition supports this really well. Basically, when you run CoreOS on EC2 now or on Google Cloud, I believe, the metadata service will go and fetch various pieces of metadata about the machines you're running on. We can build a custom version of that for bare metal, so it can just ask the config service what its metadata is, and very similarly to what you get on cloud providers, we'll just write that to a known location so that all of your systemd units that you write can just reference that to get the machine data. So that can be a solution so that you don't have to hard code information like you do now in the examples. This is just to get things working. And then features, adoption, we should probably migrate some of the cloud config stuff to Ignition to start taking advantage of its features, adding GNU grub support, show some more Rocket examples, because I got that working yesterday, and more cluster examples, show installs to disk, and eventually have an example that does distributed trusted computing end-to-end. So please, yeah, just try this project out and let us know what you think of it. The easiest way to try it is on Rocket and Docker on your machine, or if you have physical machines, you can try it too. So, yeah. Do you have questions? Yeah. IPMI to power cycle? Maybe. I don't know what the integration would necessarily be. I would love to hear more about those. What ideas you have? I think I should just have a review period to look at all those existing things that people like, and try to take borrow features or integrate with them, depending on what's popular, what people want to use. So please email me. That's a good point. Yeah, this sort of the auto discovery mechanisms is what you're asking about. Okay, that's a good one. I don't have a solution. Sure. Yeah. So if you strip it all down, you can view this as just providing the right ignition configs to machines, which is sort of leveraging a CoreOS feature in a better way. And the other purpose of the project is to provide a bunch of guides about common things that people want to do on bare metal and have guidelines for those. So if you're anything with Cobbler or other stuff could make their way into that repository, and how we could have guides on how to use those particular tools too. All sorts of guides around how to do that would be fantastic. I don't have a direct feature by feature comparison. It's way too early for me to have that. Sorry. Yeah, maybe that's something I'll look into in a little more detail. Yeah, this was about getting as quickly as possible getting some configurations that would set up Kubernetes as examples for people to try out, and getting those to work locally with CNI and with Rocket and Docker examples to run everything as a container. I'm sure that is all achievable with those systems too, and there's a lot of overlap. But I just chose this route because it was familiar. Yeah, please try it out.
All right, well, thanks everybody for coming to the first 2016 CoreOS Meetup. We'll hang out for a few minutes. How long?
Till 9? Okay. So, quite a few minutes. I think we're pretty close on the beer, but there's a couple left, so it's a race to the back. And